Today I have for you all the sequence squeeze theorem. That is that if an and bn and xn are all sequences where xn is trapped between an and bn and bn both go to the same thing, then x has to go to that thing. We can draw a little diagram here. So if we've got our little boom, and we maybe do an in this orange, and we maybe have bn in this light blue, and we have L right here. Boop, 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 boop. And then xn is bouncing around all in here somewhere, but it has to stay between an and bn. I guess the way I wrote it down, this should be an. Whoops, this should be an. And this should be bn. Right, and the yellow is xn. So bn and an are both going to this L, and xn is between them, and so it literally has to get squished onto L. That's the theorem. So some things we know are, since an goes to L and bn goes to L, I'm going to make a little shortcut here. First, we're going to let epsilon be greater than 0. Since an and bn both go to L, there's some big N, after which both the an's minus L and the bn's minus L are smaller than epsilon, because I can just choose n1 to work for this and n2 to work for this, and then choose n to be the bigger of the two. Well, what that actually means is then that negative epsilon and an minus L and epsilon are in this relationship. An minus L is between negative epsilon and epsilon, and also negative epsilon less than bn minus L, which is less than epsilon. Since for all n, xn is between an and bn, that means that an minus L and bn minus L are between, or bound xn minus L. Okay, but what is this thing? This thing is less than epsilon, but also negative epsilon is less than this thing over here. And that means the negative epsilon is less than xn minus L, which is less than epsilon. And that means absolute value xn minus L is less than epsilon. Boom, done. Eventually, all the xn's are epsilon close to L. You can maybe have an example of how to use this. So here's an exercise or an example using this. Prove that 1 over n squared goes to 0 using the sequence squeeze. Well, we know that 1 over n goes to 0, and we know that the constant sequence 0 goes to 0, and 1 over n squared is always between 0 and 1 over n, so 1 over n squared goes to 0. Whatever. Great. Okay, next we just have a definition. We have the definition of monotone sequences, which we're going to have to know. So a sequence, we call it monotone increasing if every term is at most the one after it. So we can maybe draw a little graph. Increasing would look something like this. And then several can be at the same height, and then can start going up. Similarly, a sequence is monotone decreasing if every term is greater than or equal to the one after it. So maybe a monotone decreasing sequence looks something like this. If a sequence is either one of these, you call it monotone. So if it's either monotone increasing or monotone decreasing, you can just call it monotone. And sometimes that's good enough. Here's what we need this for. Something very useful, the Monotone Convergence Theorem. Suppose AN is monotone, then it converges if and only if it's bounded. Okay, we can go this way first. So we can imagine, we can draw a little graph. Let's just assume it's monotone increasing. If there's a bound, like say this thing is a bound, then eventually we keep going up and 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 up, and we're going to hit this ceiling, and we're going to converge to this thing if this is actually soup of AN, such that N is in N, the soup of this set. And similarly, if it were decreasing, it would decrease to the inf of that set. All right, so let's suppose AN converges. By previous video, AN is bounded. Boom, done, easy. Convergent sequences are bounded. The other way is more interesting. So suppose AN is bounded monotone. Let's just assume increasing. Okay, it's the same for decreasing, just upside down. And let L equal soup AN for N and N. So this is just the least upper bound of the set of all the terms in the sequence. Let epsilon be greater than 0. I'm going to want that AN approaches L. And that's if and only if. So what we want is eventually AN minus L to be less than epsilon. By suprema analytically, there exists an element of this set that's within epsilon of the soup. So there is some N such that the distance between AN and L is less than epsilon. Then, since N plus M is greater than or equal to AN for all M greater than 0, we have that the distance between A, N, or maybe I should call this capital N. Yeah. There we go. So beyond this capital N threshold, every AN is at least a capital N. So then, distance between AN minus L, well, L is greater than every AN, greater than or equal to. So over here, we know L is greater than or equal to AN, and we also know that AN is greater than or equal to A cap N. So this distance right here has to be at most AN minus L, and that has to be less than epsilon. So boom, there you go. So but just by suprema analytically, since this thing is the least upper bound of the elements in the set, given any epsilon, there's an element of the set within epsilon of the upper bound. And then that means since the sequence is monotonic increasing, so maybe this right here was our A capital N, all of these are even closer to L. So the distance between an and L has to be bounded by the distance between a cap n and L. And that was bounded by epsilon. Okay, so that means an approaches L. It's pretty much the same thing for going the other way. It's just upside down. You can do that by yourself, I'm sure. You're a smart cookie. Is that all I have? Okay, I think that's all I have. Hold on, I can do a little more. Okay, this is one of the propositions in the book. If big S is a subset of the real numbers and it's bounded above, and it's not the empty set, then there's a sequence contained in S such that an approaches the supremum of S. Now this is really easy. If S contains its supremum, you can just do the constant sequence of the supremum and then the supremum and then the supremum, just a constant sequence, and that approaches the supremum. But if it doesn't, it's a different story. Let's use orange. By suprema analytically, for any n, there is some an, which is in S, such that sup of S minus 1 over n is less than or equal to an. So for each n, choose such an an, then an approaches sup S. Well, how do we know this? We're going to do, let's use purple. Because limit as n goes to infinity of sup S minus 1 over n should then be less than or equal to limit as n goes to infinity of an. Limit laws. This as a constant sequence converges, and this converges to 0. So that means sup S is less than or equal to limit as n goes to infinity of an. We also know that this is less than or equal to sup S because every single term of this sequence is less than or equal to the sup. So the limit of the sequence has to also be less than or equal to the sup. And we've just squeezed limit as n goes to infinity of an in between sup S and sup S. So that means actually sup S is equal to limit of an. Great. Okay, if you didn't like that for some reason, I've got a different proof. I'm going to call L sup S. We're going to use epsilon language. So we're going to let epsilon be greater than 0. Then by the Archimedean property, there exists some n such that 1 over n is less than epsilon. We also know that a capital N, the distance between this and L, well, that was designed to be less than or equal to 1 over n, which is less than epsilon. And that means that for all n bigger than big N, an minus L, well, this was designed to be less than or equal to 1 over little n, which is less than or equal to 1 over cap n, because n is bigger than big N, and that's less than epsilon. Done. Like and subscribe.